Alright, so now we're actually going to use the kNN lazy learning method and apply it to the breast cancer tumor database that's provided by Wisconsin University. And you can get the data from this link over here, and I'll include that in the YouTube description. So the first thing that you want to do is, once you find the CSV file, is create a read the CSV, right? And we're gonna, it's called WSC underscore BC data.csv, and we're gonna put strings as factors equals to false. All right, perfect. All right, so now let's view this file. So view cbdcd, and here we have all of the data that's included within this file. So you can see IDs here, and that's not particularly relevant. It's just a patient ID, and I'll show you how to get rid of that. So with step 2, what you want to do is explore and prepare the data. All right, so in order to do this, let's look at the structure of the data. So as you can see, it has all of these features, and we realized that IDs weren't particularly useful. So how about we take that out? We're gonna store our new data from the current data without the first section, and that's the ID section. All right. So when we look at the structure now, we see that ID isn't the first, and diagnoses is. So M here, we can assume, stands for malignant. And there's probably benign as well, but we can actually see how many of each there are by using the table function on the subset of diagnoses. And we can see that there's 357 benign and 212 malignant. How about we assign factors to these two and assign them labels that are better than B and M?
Alright, so here's how we do it. We use the factor function on the diagnoses with the levels of B and M, and we'll label it benign and malignant. So let's run that. Alright, now we probably want probabilities associated with these two. So we're going to assign this prob object. We'll work inside out. So we have these diagnoses, we have the table, and the output of the table is what you saw, and we're going to use prob table. Now, that's what you're going to get. You're going to get about 0.627 and 0.372, and that's a percentage. So let's run this whole thing, and we're going to round that number to the first decimal place, and we're going to get an
indicator of what percentage of tumors are benign and malignant. The reason you want to know this information is to see if you can actually build a training and test set based on your model that you have. Say all of these were benign or all of these were malignant, you basically wouldn't have a way to predict one or the other. So you need some sort of representative data set to allow you to predict what you actually want. Alright, so now we're going to subset some features of interest in order to see how these some statistics around these variables to better understand a little bit more about the data than what we would get just from just looking at this giant table here. So let's look at radius mean, area mean, and smoothness mean, and we'll add that to features, and we'll use a summary of that subset, and what we get is the minimum and maximum values, the means, the medians, etc. And if you recall from the theory portion of the kNN algorithm, is that we have to make sure all of these features are normalized, either 0 to 10 or 0 to 1. Also, there's things like Z-score standardizations, which I'll talk to you about later, but we want to make sure that there's no one feature that's greatly overcompensating or undercompensating in terms of the distance calculation for the kNN. So the next thing that we're going to have to do is actually create a normalization function. And this is the first function we're actually going to make, and so I'll walk you through it. Alright, so we're just going to use the most basic normalization, which I described in the theory section, and that's using the maximum and minimum points. So to this, to normalize, we're going to add the function x, which is what you're going to be inputting into this function, and it is going to return x minus the minimum of x divided by the maximum of x minus the minimum of x. And it's going to do this for the entire vector or whatever object that you apply into this. So let's create that function. And now we have to test that function in order to make sure that it does exactly what we intended it to do, and then we can apply it to our data set. So I encourage you to actually do this and test that it can be done yourself and not take my word for it. But let's walk through this together. So let's normalize, let's say 1, 2, 3, 4, 5. Now let's try to predict the output of this before it happens. Since we're normalizing between 0 and 1, what we want is 0 and this maximum value here to be 1. So what can we expect in, say, the second place if we're going to put this number in? We're going to put 2 in here minus the minimum. That's going to be 2 minus 1. So you have 1 in the numerator. The maximum minus the minimum is going to be 5 minus 1. So that's 4. So it's going to be 0.25. So that's what we'd expect in the second spot. Now let's see if this actually follows through. Alright, so it does. So what we have here is 0 for the first place, 0.25, 0.5, 0.75, and 1. Now we need to ensure that this function works for more than just 1, 2, 3, 4, and 5. Let's see if we can normalize something of maybe an order of magnitude greater. So let's do 10, 20, 30, 40, and 50. Alright, so as you can see, it normalized this function as well with a minimum of 0 and a maximum of 1. And we have the same normalization criteria that we were setting out for. Now we can apply this to the data set that we have, and that's what we're going to do shortly. Alright, so let's normalize our data set. Let's call it WBCD underscore N. Alright, and we're going to use the lapply function. So as a data frame, we're going to lapply WBCD 2 to 31, comma, normalize. Now what is this going to do? It's going to apply the normalization function to WBCD as a data frame into this new object that we're creating. That's going to be the normalized data frame. So you might be wondering why 2 to 31. If you recall, the first column here is diagnoses, and you can't really normalize these factors, but all of these other ones are numeric, and therefore they should be normalized to the same level. So let's do that, and that works. Wonderful. So, of course, there's two ways to view if your data actually got normalized. So we can actually view the actual new data frame that we created, and we see no numbers above 1, but what would be better than doing that is using the summary. So let's use summary of WBCD underscore N, and why don't we take the subset of the features that we were first looking at above, and we'll see if those are now normalized. Perfect. So what we see here is exactly what we wanted. We have a minimum of 0 across the board and a maximum of 1 across the board. The means and standard deviations are going to be different, same with the first and third quartiles, but it's normalized within this range, and that's perfect. For the next part that we're going to do is training the model. So we're going to train our kNN model. So the basic premise of training a model is you want to split up your data into a training set and a test set. You're going to build a model on the training set and see how well it predicts the test set. So you can split it however you please. However, it's recommended as a starting point, maybe split it in half. And thankfully, the data frame that we're using is already randomized, so we don't need to randomize it any further. But if it's not randomized, you need to ensure that you have a random sample for your training and testing set. But since this is randomized, we can build the training set and the testing set right away. So how about we do that? And BCD, BCDN normalized, and we're going to split the 569 directly in half, and that's going to give us 100. See 1 to 169 for the training set, and we're going to make a test set as well. And we're going to call this test, and we're going to use the same method. And we're going to go from 1 plus the higher level there, so that's going to be 50 to 569, and comma, enter. All right, so now we've subsetted our data into two different sets. This is basically split the data in half. We're going to be building the model on this training set and seeing how well it predicts this test set. In reality, once you keep using machine learning algorithms, your test sets are eventually going to become real life data that's going to come in. And if you have a good model that you've built up, your test set that's real life data is going to be very reproducible based on the model that you built. But this is a good place to start, because if your training set can predict the rest of the split your test set, then you have a good foundation to move forward. Okay, so as you can see, we split it up row-wise. We're going to need labels, what we're going to predict, and that's diagnoses, and that's in the first column. So what we're going to do is we're going to create labels for these. So why don't we do that, and then we'll call it labels, and we're going to go W, B, C, D. Let's do 1, 2, 4, 69, and the first column, which is the diagnoses, and that should work perfectly. Similarly, we're going to be doing that with the... So perfect. That's exactly what we did here with the test set. Similarly, we took the rows of the test set and the diagnoses column. Now, we want to train them all, and you're going to see how amazing this actually is at its predicting power. So in order to train the model, you should already have this installed in your R package, but if you don't, you can go to install.packages and get the class package and use library class to load it up. And okay, so let's actually use the kNN algorithm, which is included in that package. So test, and this is the prediction. We're going to assign the kNN, and the first thing that we have to do is set our training set, and our training set is the WBCD train, comma, and the test set is going to be the WBCD test. The class, what we're predicting, is going to be WBCD underscore train labels, and then, sorry, I missed a comma, and we're going to use a k value of 21. The k value of 21 is the root of 569 approximately, so that's what we're using here. I'll show you the output or the evaluation of the performance of various k values later on, and we can discuss the bias variance trade-off again once we do that. But first, let's do this and see how our model actually performs. So that's step 4, evaluation model performance. All right, let's just comment that. Alright, so last time we used cross tables to compare conservative car colors across various models of used cars, and this time we're going to actually use it to check how well our training kNN model with k equals 21 actually predicted whether a tumor, based on the 30 or so features that we had, was benign or malignant. So in case you don't have it already, install the package 2 models and load it up. and we're going to get this cross table here. And I'm going to tell you how to interpret this cross table. So in the labels, this is what we wanted to predict, benign and malignant, and this is what our model predicted, benign and malignant. So our model predicted that there was a total of 79 benign tumors, of which we accurately predicted that 77 would be benign, and they actually were benign. However, 2 we predicted would be benign, but they were really malignant. So this is a true negative, and this is a false negative. This is a dangerous false negative because you're basically saying 1 in 50 times you're going to say someone has a benign tumor when they really have a cancerous tumor, and that's potentially risky. But the accuracy is still quite astounding. We predicted no false positives. That's to say, we predicted that no tumors would be cancerous when they actually weren't, and every single tumor that we predicted would be a cancerous malignant tumor was a cancerous malignant tumor. So as you can see, in total, everything adds up to 100%, as we would expect, and we have a total accuracy of 98%, with the 2% being this false negative over here. So now we're going to look at improving the model performance, maybe try out a different way of normalization and some different k-values, and see how that actually affects our models. So there's a few ways that you can improve the model's performance. Perhaps one is using a different normalization method. So we can create use a z-score normalization, which is included within the R package. You can use the scale function, and instead of lapply, you can just as data frame to this new object that we're going to call z underscore z, and that's going to be the standardized z-score of this data set. We're going to take out the first column, which is the diagnoses. And basically what this summary does is it shows you those features that we're interested in: radius, area, smoothness as an example. Unlike the min-max normalization where it goes from 0 to 1, this is actually going to have a mean of 0 and have a standard distribution around the mean where values greater than 3 and less than -3 are extremely rare. And most of the data points, as you can see, within the first and third quartile are very close to the mean. And you can use different normalization methods to see how it improves. Also, you can see how different k-values affect your model's performance. So I'm going to show you the results from various different methods on improving the model's performance and what the actual output is, and we can discuss from there. Alright, so let's discuss the actual z-score normalization results. So as you can see, the model performance actually decreased from just the min-max normalization from 98% to 95%. But what's potentially dangerous here is that this value increased from 2 to 5. So we're actually predicting that 3 more benign tumors, 3 more cancerous tumors were benign than we expected, and that's a potentially dangerous false negative. If we look at various k-values, we can see ranging from low to high that the best k-values are 5 and 21, and this just goes to show you that the root of the k-value is a good starting point. It is a bit more of an art than a science, but it's a good starting point. You should test multiple k-values to see what kind of indicators you get. The danger with small k-values like 1 and 5, even though one's pretty bad in general, but 5 seems good, is that with a different set of data, you're going to get a different number. These k-values are too susceptible to the influence of noise around their parameters, so something around the root of k would be a good starting point. And look around there to see that you have some kind of optimal solution moving forward and with your predictive model.